particle in a central field. Now, what do I mean by a central field? A central field is any field where the force is a function of R, okay? It could be like a spring force, which is minus kx or R, or it could be like a gravitational potential. So the first example is of a mass spring system. And the other one is obviously gravitational. So we'll talk more about them, but just to introduce you to this idea. When you're dealing with particles in a central field, you usually deal with them in polar coordinates. And we defined our polar coordinates as I phi, R phi, or you could define them as R theta to match them with things that we have just done above. So this is kind of like if you have a gravitational field, for example, it will be like Earth moving around the sun with an arc as the radius varies. Okay, so now remember, in the simple pendulum, R was equal to L and L dot was 0. In this case, R may not necessarily be a constant. Okay? So then you cannot say R dot equals 0 and move on. So how do we deal with problems like this? Well, first of all, we are going to write our Lagrangian. So what will our Lagrangian look like? And V will be a function of, and how did we define the kinetic energy for a polar coordinate?
R dot squared plus R squared theta dot squared.
Minus V as a function of R. Now note, I am not actually defining V as a function of R, I'm just leaving it alone. So whatever V we will get for the particular problem you have, we're going to replace it later. And I want you to take your steps out. And then on this side, we're going to do the Hamiltonian way. Okay, so I want you to, on your left side, put Lagrange. On your right paper, put Hamiltonian. Okay, so when we are looking at the Lagrange way, we have two coordinates, right? R and theta. How many equations should we have? Good. Which two? One corresponding to R and one corresponding to theta. Okay, so the one corresponding to R is forever and now going to be called the radial Lagrange equation. And this will be for R. The other one that depends on theta is called the angular Lagrange equation, and it will be a function of theta. I'll keep the Lagrangian in your view. But my radial equation will look something like this. Partial L over partial R dot minus partial L over partial R equals 0. D over dt of partial L over partial theta dot minus partial L over partial theta equals 0. Do you see now why we were using partials? Because we're only taking the derivative over R. We're only taking the derivative over theta. Everybody done? The next step? Okay, what does that look like? So this would be d over dt mr dot minus mr theta dot squared plus partial v over partial r equals 0.
Wouldn't it be minus?
Does everybody realize why I have a mr theta dot squared there?
Yes.
Okay, so then may I write this as mr double dot minus mr theta dot squared minus f as a function of r equals 0. Because did we not say that f of r could be written as partial v over partial r with a minus sign? Okay, then this means I can write d over dt mr squared theta dot minus 0 equals 0. There is no term that has theta only, is there? Good. So then I can write d over dt of mr squared theta dot equals 0, which I can also say mr squared theta dot is a constant. I can also say from here, can I say m2r r dot theta dot plus mr squared theta double dot equals 0. Since m is not equals to 0 and r is not equals to 0, may I rewrite this as 2r dot theta dot plus r theta double dot equals 0? Yes.
Do you need to have that first?
Oh, yes, I do not. Good catch. Yes.
I wasn't following. Why were you able to do that?
Which part?
So were you able to put up m into the parentheses?
Oh, to see this m is here?
Yeah.
I can take it common out.
Mm-hmm.
Then I'm just left with. Let me give myself some room. Can I write md over dt of r squared theta dot equals 0? So then that m stays there. Remember I said r is a variable and theta dot is also a variable. So now you have to differentiate them both. It'll be 2r r dot theta dot for when you differentiate it over r, and then it'll be r squared alone and theta double dot when you differentiate it over theta dot.